Let's take a look at section 4.3. Now, what I really like about this lecture is that it's finally one where what we've been doing in 4.1 and 4.2, introducing like parts of a hypothesis test, is that we finally get to do a few examples where we put all of it together. Now, remember the whole point of a hypothesis test is there's two different arguments, and we're trying to find enough evidence for the alternative. Um, Now, when we are seeing which argument seems to be more likely to be true, it is based on a sample. Now, when that sample comes back and we got the result, if we want the alternative argument to win, we're hoping that that sample, if it's there to back up the alternative, is that it was not a fluke. That is where the p-value comes in, showing us a way of measuring how likely something was to have been a fluke or not. There's just a recall of the definition of the p-value. Again, it's the idea that we're assuming that the null hypothesis is true, only in hopes that we can find a way to contradict it. Now, as far as our notes, the results of a hypothesis test, again, thinking about the conclusion, you've done an average, you've done a proportion, and whenever you get that number, we say that it is. We say when we're doing a hypothesis test. Sometimes they'll also go by the name of a statistical test. Again, the statistical coming from the idea that it's the argument is being based off of a sample. We say that the results of a hypothesis test are statistically significant if the p-value is small. We're going to say more formally that it's less than what we're going to call the level of significance. You're going to hear us saying the word alpha. All right, now alpha, where that's coming from, is the Greek letter alpha. And usually, sort of like when you're first starting hypothesis test or reading articles, a lot of them are going to use a 5% level of significance. And what we're oftentimes going to be doing is looking at purely in the decimal form. Now, the smaller the p-value, the better. Because again, if you have done something spectacular and someone says, "Oh, that was probably just a fluke," that's their way of saying, they don't have a lot of confidence in your ability to do that again and again and again. So if something has a small p-value, the chances of it having happened just by random chance or it being a fluke are really small. And specifically, we'd say, there's a less than 5% chance it was a fluke. In other words, it might routinely happen again and again and again. Now, one of the skills that you're going to need as we get to the conclusion of a hypothesis test is to be able to compare whether the p-value for a result is it could be called statistically significant. And that is going to be that you're going to compare it to alpha. So what I did here is an example of a test that they did. That's the results, everything's all available. The p-value, the level of significance is going to be 5%. Now, in this study, what they were doing is their cases were lemurs. And what they were doing is testing to see whether this ingredient, known as resveratrol, it's an ingredient like in red wine. So they were seeing what kind of effect it would have on the lemurs, but not just on one thing. It was actually three different things. I'm just going to put a lasso around all of them. So it was three parallel or like simultaneous tests that were happening. One of them was to see whether that ingredient would cause their mean resting metabolic rate to be higher. Another test was to see whether it would lower their mean body mass. And then a third one was to see whether it would have any effect on their locomotor activity. So three separate tests, and all three of them had their results. And in terms of any of them showing something being higher, lower, or differs, they each have a corresponding p-value. So for the first test about the increase in their mean resting metabolic rate, the p-value came back as being 0.013. Now, that p value, what you'll do at the end of a test is you'll compare that to alpha. And alpha, as mentioned already, in this one, they're saying do a 5% level of significance, meaning check to see if there's a less than 5% chance that it was a fluke. So the p value is 0.013. Alpha is 5%. Again, we're usually going to do it in just purely decimal form. And in this one, you can see that the p value of 0.013 is smaller than 0.05. So in that case, yes, if there was an increase or if they did see evidence that the mean resting metabolic rate was higher, there's a pretty good chance that that was not a fluke, or very, very small chance it was a fluke. And so they would say that yes, this result is significant. In other words, if they were to do the test maybe a second time with lemurs, they would once again see that the resveratrol leads to a higher resting metabolic rate. Now, the second test was to see whether it would lower their mean body mass. And the p value that they got was 0.007. Again, each time that you are checking to see whether a result was significant or not, you're going to compare it to your alpha, your level of significance. And you can see in this one here as well that the p-value was smaller. So there is also a less than 5% chance that this was a fluke. So you would once again say that yes, this result would be considered significant. Now on the homework, you don't have to put yes, significant. By just putting the word yes, you're saying that the result was significant. That if they were to do the test again, they would see once again the mean body mass being lowered again. I went ahead and included the third one here, part C. They were checking to see whether there was any kind of change in the locomotor activity. P-value came out to be 0.98. Again, each time that you get one of these p-values, you're going to compare it to alpha, and you can see here that that p-value is really large. There's a much higher than 5% chance that that was a fluke. Actually, there's like a 98% chance that if they did see any kind of change in the locomotor activity, big time could have just been a fluke. That if they were to do it again, it would not always be that that's the outcome. So I would say no, it's not significant. It's not something that you would want to bet on. And that's what we do. That's going to be one of the little small skills that we need to help us make our conclusion to hypothesis test, whether something was significant, not significant. And 5% is usually the articles they're going to use. But you can also at times use either a 1%, 10%. So we'll do more of 1%, 10% when we get into the later parts of chapter 4. But just to throw one in right now, 1%, anything needing to be less than 1% chance of that it was a fluke, that would be your alpha. And I'm going to put it right here. But as a decimal, that would be 0.01. And if you look up there at all three of these p-values, mainly what this last one is asking you, which one of those would be significant, or in other words, which of those would also still be smaller than a 1% chance that it was a fluke. So you're just looking for which p-value there is the smallest, or which decimal is the smallest, and it would be that one right there. Yeah, 0.007 is very, very small number. So the p-value of 0.007 is smaller than 0.1. So B would be the result that shows the strongest evidence that it was significant. Now, if you ever are doing one of these and ever having any kind of doubts about comparing two decimals, here I'll go back up to number one at part A. Right here, if there's anyone who ever is like, I don't like comparing three decimal places to just two, you're always more than welcome to put in an extra zero there. That way you can see that 013 is smaller than 050. Just a little tip, just in case you ever need a little extra. So like this one too, like 007 is smaller than 010. Now, for this next part, there's just a small little like loose ends I want to double check to make sure that we don't miss. And is that going back to the randomization distribution? The whole gist of this is that the null hypothesis is what's going to be sitting in the middle as what we assume to be true, but we're actually hoping that it's not, or that we can find something to a sample that's maybe way out here or way out here as a contradiction to it, that it's wrong. And anything that's way out on these tails are the things that are going to have smaller p values. They're also going to be the things that give us stronger evidence to argue in favor of the alternative. And in 4.2, we were talking very lightly about the conclusion. Um, the conclusion is going to be one of two things whenever we talk about the formal generic conclusion. So you can remember the big thing that we're hoping to be able to do is to reject the null hypothesis, that it's wrong, which is the other person's idea, the initial statement. And we'll be able to do that anytime that the p-value is smaller than alpha, that there was a small chance that it was a fluke. Anytime that the p-value is really big, we're not going to say that the null hypothesis wins. We're not going to accept it. We're going to say, do not reject the null hypothesis, which is it sounds kind of like we're being stubborn, and that's good. That is what we are doing. We're not giving up on the alternative, but we're never ever going to say that the null hypothesis, oh, let's go and accept that it's true. No, 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 no. So by saying do not reject the null hypothesis, that is not the same thing as saying that we should accept it. I'm going to write it. No, that's not what that means. So take this for example. Suppose somebody has accused you of doing some crime, and you come to me, say, hey, Professor Mendoza, I need you to be my lawyer to try to defend me. And I say, okay, I'm going to help you out. And I spend some time collecting all the evidence, present it in front of the judge, the jury. They hear it out. And then whenever they're done, they come back and say, nope, nope, we're not going to buy it. Well, what is my job as your lawyer? All right, just think about what my job is as your defender, and that would be to find the evidence that shows that you're innocent, right, or that you're not guilty. But suppose that happens, that the judge and the jury come back and say, nope, this is not enough evidence. I'm not all of a sudden going to switch teams and say, hey, I'm going to go in and accept that you're guilty. No, I'm gonna say no. I don't have enough evidence to say that you're innocent. I'm gonna go back to the drawing board. Maybe there's something I missed. I'm gonna collect some more evidence. I'm gonna come back and try again. All right. So yeah, never ever. Same thing with hypothesis test. You either say you reject the null hypothesis, or you say you don't have enough evidence, but you never ever say you accept it. All right. We're team HA um, through and through until the day we die. Okay. Just heads up, I throw that into the like the test as a true false question. So make sure if you ever see that it says, should we accept the null hypothesis? No, say that we don't do that. Now, that's your short conclusion. So there's going to be two of them. There's going to be the short one, that's the reject or don't reject HO. But then there's going to be what we saw in 4.2, the conclusion in context, where you describe more about what the study was trying to argue for. And it's either going to be starting off that you say that there's enough evidence to support the alternative, or you're going to say, hey, we didn't win our case, or we didn't win our argument. And we say anytime we do, there's not enough evidence to reject the null hypothesis, then we'll say there's not enough evidence for the alternative. Um, Now, my answer key is going to have do not reject the null hypothesis in situations where we lose. But you can also say fail to reject. And I almost kind of like that a little bit better. The authors don't really use that. They use do not reject HO or the textbook. But fail to reject HO is, I think, also another way to say, kind of keep in mind that our goal was to try to reject it. We failed in our efforts. But let's try. This right here is just a bonus page. When I say that it's a bonus page, like it is critical that you use this when you're doing any of your hypothesis tests moving forward, because it is a sort of like a blueprint for what's going to be happening in terms of the flow of a hypothesis test. So, couple things: when you state your null, like your HO and your alternative HA, we're going to be doing it using parameters and the notation for parameters. And the reason why we use parameters like mu's and p's is because these are all meant to be arguments about all, about the entire population, like all cases, like all men, all female, all students who do this, or the average for all of them, the proportion of all of them who do this. So you always use mu's and p's, never any x bars, never any p hats. And for your null, this one here is the structure anytime that it's going to be about just a single group. And then these are the two that you use whenever you're doing means or proportions. And there's two groups involved where you're trying to say maybe both groups are the same. Someone's trying to say, the same average, same proportion for both groups. There's no difference between them. Then your alternative, sometimes it's going to be about a less than. And that would also be synonymous with doing a left tail when you're doing your p-value. Some are arguing in favor of greater than, which would be right tail when we go to calculate our p-value. And then some of them haven't specifically decided whether they want to do a less than or greater than. They just saying in general they feel like something differs. And that would be your two-tail test, where I'll just throw it right there, where you have to do times two whenever you are calculating to find your p-value. So we'll always start with that. What's the null? What's the alternative? What are the two arguments? What's going to help decide which argument holds more water or seems more plausible is we'll do a sample. And the statistic or the result from that sample is gonna guide us into which direction to go. Now you've got four of them here because these are the four main ways that we're going to be doing tests specifically for chapters 4, 5, and 6. We're going to be doing means, proportions, one group, two groups. Just keep in mind the p-value. I mean, there is a way to calculate it. It's going to be used for the purpose to help us decide whether there's enough evidence or not. But it's always the one that assumes that the null is true, at least to start the story. But then somewhere as we get through the story, the hope is to show that it's wrong. The winning side of the situation is over here. So once the result comes back and we get its p-value, if the p-value is small, then we would say that the result was statistically significant, meaning it was less likely because that was due to just being a fluke. So in those situations, we'll be able to reject the other person's argument, the null, and start to say, in conclusion, there is enough evidence for the alternative. Over here's the losing side. If ever the p-value is really big, that's going to suggest that the result was maybe just highly due to being just a fluke, not going to always be a reoccurring observation. Again, we won't accept the null hypothesis. We're going to say Do not reject it, or you can say fail. Again, my answer key is going to have do not reject. But again, if you want to use that instead, we failed to reject the null hypothesis. We wanted to, we're just not able to because our evidence isn't strong enough. So let's go and start using that in some examples, right? Some real world examples. Um, Now, on this one here, what I want you to do is pause the video, but read the prompt. And since we haven't done a whole bunch of these, I'm still going to go and just give this that word test is meant to be the statement that sets up what the two arguments are. And remember, the null is the one that always say, hey, the value for something is equal to this. But then the alternative comes along and says, no, I'm going to argue that it's maybe less than, greater than, or it differs. Now, once you read the entire prompt, you'll be able to do that. And you'll also, for B, be able to put when they did a sample, what did it say happened? Or what does it seem to be? Here's what we found out. And after, and again, I want you to pause the video, try it A and B on your own. But then also, before you go on to C, I'll go on to C with you in just a second, is to show is whenever you get this number, which one does it seem to be immediately showing to be more likely to be the truth? All right, so go ahead and pause the video and try A and B. All right, here it comes. So they did a sample, but the reason why they did a sample is because they wanted to test whether there's enough evidence that the average amount of sugar in these bottles of tea might be greater than 25. And where 25 came from is the label. The label initially said that there should be, on average, 25 grams of sugar, but maybe somebody has gotten suspicious and believes that maybe there's more than 25 grams on average in there. So that'd be your HO, your HA. We can also go ahead and just real quick label this as a right tail because we're going to be doing it greater than. When they did the sample, notice I'm putting X bar there. And also, if you're like, wait, why are we doing X bar? Because this was a sample that gave us a mean of 33.8. So the mean from the sample was 33.8. And this is one of the things I asked you to do, besides just putting your answers down, is also like which of these two does the 33.8 seem to already be supporting? That it's equal to 25 or that it's more than 25? And it is that one, right? If it had come back to be like 26, that's not bad. That's pretty close to 25. But the moment you start getting to like 28, 29, 30, 31, 32, 33, the further away you are from 25, the more that you start getting really suspicious that the label might be inaccurate. Now, if we're the ones making this bottle of tea, these bottles of tea, we're kind of hoping that this was just a fluke because we don't want to have to shut down operation and reprint labels or fix the recipe. So we're kind of hoping this was just a fluke. But when we go down here to get the p-value, they've already given us a graph that has re-randomized, a bunch of times, 1,000 times what else could have happened by random chance. And anything that's from maybe here to like about here would probably be the stuff that most likely happened by random chance. That was just a fluke. But anything on the outside probably was not a fluke. And so there's 31 and 34. So maybe 32 and 33 are right about there. 32, 33. And so 33.8 maybe right there. That'd probably be a good, reasonable spot to locate 33.8. And again, the reason why we're doing 33.8 is because we're trying to get the p value for that statistic. Like, how likely was that to have been a fluke? Well, there's nothing above it to count, but there's still three dots to the right. So the p value is the proportion of these dots that are as extreme or more extreme than what was observed. So the p value is 3 out of 1,000. And then you turn that into a decimal to get 0.003. Now, anytime that you see double zeros, that's a really small p-value. Like if this had been 3, that'd be a really big p-value. If it had been 0.03, that's small. But then anytime you have 0.003, that's a really small p-value. So there's a well, let's go on to D. Like, what do you do with the p-values? I'm just circling the level of significance. That's alpha. I'm just going to put it right here. The p-value was 0.003, and alpha is 0.5. Just like we did on the first page, you compare to see whether alpha is smaller. Excuse me, you check to see whether the p-value is smaller than alpha, and in this one it is. Like 0.003 is much, much smaller than 0.5. So a couple ways that we could describe like what just happened here is uh, that the result was significant. I'm going to put it really small. It's not necessary that we have to write this. Significant, that it was not a fluke, or more specific, like it's very small chance that it was a fluke. Now, for the conclusions, they call it the generic conclusion, or sometimes they'll say the formal generic conclusion is we can reject the null hypothesis. So, in other words, this just died because the 33.8, which is already immediately backing up the idea that there's more than 25 grams, also has behind its conclusion that it was probably not a fluke. Right. So if they did want to do another sample of these bottles of tea, it would probably once again show up to be a, yeah, this there's too much sugar in these bottles. The label's wrong. So we get to reject the null hypothesis, and then for your conclusion and context, we're going to say there is enough evidence to support. And then now we're going to put what the HA was arguing for, which is that mu greater than 25, that the average amount of sugar is greater than 25. And you're welcome to reuse their words. You can see it up there. They have like the average amount of sugar per bottle is greater than 25. The evidence supports that idea. There's enough evidence to support that the average sugar per bottle is greater than 25 grams. Now, the reason why it's important to end with that conclusion with the words is because if you look at everything that we've done before up to this point, there's nothing really in what I circled there that tells us what the study was about. So all we would see is mu 25, 25, 338, this p value, have no idea what the study was about. So the ending is really just to put a recap that someone was suspicious and found out that, yeah, maybe there's too much sugar in there. So they have an issue. They have to either fix their recipe or um, reprint new labels and say new and improved recipe now with 33 grams of sugar. But again, before having them go through all the heartache and ordeal of fixing their recipe is, we checked that sample was probably not a fluke. All right, let's try a couple more here. All right, we got example 4, example 3. Example 3 is going to be a good one to also do look at averages for two groups. Now, in this one, it says they did a sample and the mean was 12.4 for exercise, and that was for 20 males, and it was 9.3 hours of exercise each week for females. And here's the test. They want to test whether there's evidence that the mean time spent exercising differs between males and females. So, based on those samples, is that enough to say that males exercise more than females, or vice versa? Now, I put the box around the word test, and again, I want you to just take a few moments, maybe pause the video, and write what would be the HO and the HA for this. And again, hopefully you've had a chance to do your 4.1 homework. I encourage you to do that before you get too much into 4.2, 4.3. But the keywords are there. Got mean, differs, male, female. Keep in mind that the null always does an equal sign. And since we've got two groups about averages, we're going to be doing mu. So this is the reason why we're doing mu is because we're really trying to do this a big statement about all men and all females who exercise. And maybe they exercise about the same, but someone wants to argue that the average amount of exercise per week for male and female that they differ. I'm just going to put a little note that would be considered a two-tail test. So they're not specifically saying that male is more or that female is less. It's just saying that they're not the same. Now it says calculate the sample means, male minus female, and give notation. So that right there takes care of the notation. It's the sample mean for male minus the sample mean for females. And that's that information that they gave up there. They talked about how that was 12.4 was the result for male and 9.4 was for female. And then you would just go and subtract those. And that 3 is our statistic. And if you want, you could put a little note because of the way that we subtracted this, we did male minus female, and we came up with a positive 3, is to suggest that male is higher by about 3 hours. Again, some might want to just stop there and say, well, there you go. We got evidence that males work out more than females. But we can check to see whether this was a fluke or not. Now, in order to do that, sometimes it's us counting the dots, sometimes it's us using stat key. This is one where we're going to use stat key. Here's where we're going to go. Difference in means. Going to do a randomization. And then the study is this one about exercise hours, male versus female. Now, because of this being stat key, and because of this being based off a randomization, you and I will not get the exact same p-value, but they should be pretty close. So let's go over to stat key. This is our chapter 4 stuff. You could see the one that's got tests for difference in means because we're doing mean for female versus mean for male. And then on the drop down, as you go down a little bit, you should see one that says the exercise hours, male versus female. And you'll see that it's saying exactly what the handout said. Female was 9.4, male was 12.4, male was higher by 3. And now we want to see if that 3 was a fluke or not. Like, is there evidence that males really do, on average, work out more than females? So when you're ready, you'll go ahead and click your 1000, and that's going to bootstrap to see 1000 times what else could have happened by random chance. If the null is true, what might happen? So there's my 1000. And to get the p-value, since this is a two-tailed, not just left, not just right, we're going to click on the two-tail. Now you can see over here, as well as over here, that it's got that default p-value that I mentioned last time of 0.025. But the reason why that always starts off is because Stacky is immediately going to start counting the dots for some statistic. And it might already be the statistic that you need, but you always need to make sure that you manually down at the bottom put your statistic where it needs to go. So you got negatives over here, but we have a positive 3. And so right there where you see on my screen the 4.5, you're going to click on that and you're going to put in the 3. Now, if your stat key is already showing 3 down there, don't believe it. It has not accurately counted the dots the way that it should. So I'm going to go ahead and do it right here at the bottom. 4.5, I'm going to click that. And I'm going to change it to 3.0. You can also just put 3 and click OK or hit enter. And now it is counting the dots that are as extreme or more extreme. So there's my p-value of 0.083. But because of it being a two-tail, because it wasn't specifically saying less than or greater than, it's one of those two things is what the argument is saying. You need to double that times 2. But whatever you got. So I got 0.083. If you got like 0.09 or even like 0.10 something, like you're good. And the reason why I say you're good, I'm going to go ahead and do it. I'm going to go back over to my 0.089 p-value 0.089. But then I got to remember, just for the two tails, to double it. So if it had strictly like less than, you don't have to do this. But we do, since it's a two tail. So you're going to get a really big p-value of 0. I got 0.178. If you got something like 0.2 something or 0.189, like you're good. All what we need from here is that if that's my p-value or whatever you got, whatever you have for your p-value, if you compare it to alpha, what should happen, and they want us to again just reuse the 5%, you can see that regardless of your p-value being a little bit different than mine, that they're all going to be on the side of being too big. Again, we would be saying that this result is significant if it had been smaller, like a less than 5% chance that it was a fluke. But the p-value that I have here is saying that there's a 17, almost 18% chance that it was a fluke. What being a fluke, that males exercise more? That's what the sample said, but Stacky's hinted that was very, very a big chance that was a fluke. And anytime the p-value is really big, this will be our conclusion, our formal generic, or short conclusion. Uh, you could put do not reject HO, or you could put fail to reject HO, and say in conclusion, the longer conclusion, there is not enough evidence to support that, and then we're going to go talk about this again. That the average, there's not enough evidence that the average amount of exercise for males, that it differs from the average amount of females. And you're welcome to reuse the words that are in what was being tested. All right, it's right up here that the mean time spent exercising differs between males and females. There's not enough evidence to support that idea. I'm going to go and write that down. It's a conclusion in context. There's not enough evidence to support that the mean time spent exercising differs between males and females. So, in other words, if they were to redo this study, there's a pretty good chance that it could completely flip, that males don't come out on top again, that maybe females end up showing that they exercise more or that they're the same. All right. Well, let's try another one. Again, what I'm hoping happens is that as we do more of these hypothesis tests, that it slowly grows on you as feeling like a routine, that there's always an HO, an HA that are the two arguments, and that it's the HA that we're trying to argue in favor of, that there's always some statistic that comes from a sample that they actually did to see which argument seems to be more likely true. But go ahead and read example 4. Again, that word test is meant to give you whether it's about p's or mu's, whether it's less than, greater than, differs. And then B, I want you to also go to do B, which is they're going to have you do, and you'll see in a second who once you read it, you'll see there's a proportion for delta, there's a proportion for united, and they want you to subtract those. But what I would recommend you do whenever you do the proportions, go and switch them to just regular decimals, which would be divide by 100. Okay, let me be quiet a little bit so you can write the HOHA. You can pause the video and then also go ahead and do the delta's proportion minus United's proportion, and then I'll pick up with you from there. All right, so here it comes. They wanted to test whether there's evidence that the proportion for delta, just going to underline the D, is less than the proportion for United. Now, what the null is going to assume is that the proportion for delta is the same as the proportion for United. That when it comes to who shows up more late or has more late arrivals, that they're both just as guilty of having the same amount of late arrivals. But somebody wants to argue that deltas may be better. That if you choose to fly with delta, that maybe less often they're not going to have as many planes showing up late as there is for the United. And you don't have to put this on your homework, but it might be a good idea that anytime that you doing your less than, greater than differs, that you put left tail, right tail, two tail. Less than would be a left tail. Now, for these actual, like what happened when they did the data, they had a proportion or sample proportion for delta, a sample proportion for United, and I went ahead and put in there to do delta first, which is the 047 minus the 0.07. And the reason why I put that in there, because does it matter which group you put first and second? Part of me wants to say no, because either way you're going to get the same p-value. But then part of me wants to say yes, it does matter, because if you're doing a less than test, it would be nice to have that matched up with a negative rather than a positive. So doing it this way, or again, I already did it, but I'm gonna do it one more time. 0.047 minus 0.07, you get negative 0.023. And that right there is the statistic. And they say it right here. That's the statistic. But that's what we want to go get a p-value for, to see whether what was observed was maybe just a fluke. So we're going to go over to Statkey. Uh, you can see the guidance here that we're going to do difference in proportions for hypothesis tests, and that this is the name of the data set. Late arrivals, fourth edition, Delta versus United 2024. All right, so let me go there. Again, keep in mind what our statistic is. Let me put a little equal sign right here. Yeah, it's negative 0.023. I'm going to go ahead and get to the homepage of Statkey, switch over to the one that's difference in proportions. On the drop down, there it is. You can already see it. Late arrivals, fourth edition, Delta versus United 2024. There's that negative 0.023, which we calculated. They already calculated here. We want to see, this is saying that Delta is better. Delta has 2% less late arrivals than United. But let's see if it was a fluke. You're going to start off by re-randomizing 1,000. Like, what else could have happened just by random chance? You can see in the center is 0, which is saying that both airlines have the same amount of late arrivals, or that there's no difference. Then you're going to click on the left tail, because we're doing a less than test. And there's that default p-value. It always shows up 0.025, because it's going to count the dots for some statistic automatically, but it might not necessarily be the statistic that you're interested in, which it's not. We want to know what's the p-value for negative 0.023. Now, even if yours already has a negative 0.023, don't believe Stacky that it counted things the way that you actually needed to. Always manually click on it and type it in yourself. Negative 0.023. Negative 0.023. Click OK. Yeah, so whatever statistic you have right there in that bottom right corner, and don't do these. Don't get confused with the randomization sample, the original sample. And so I got it down there, negative 0.023. You can see that Stacky is now counting the dots that are above it and to the left. And it's not, if it's not counting the dots perfectly for you, that's okay. As long as you manually put it in there, the p-value is right above 0.021. 0.021. Yep, that's what it is. 0. And that one we don't need a double, because we were only strictly doing that it's less than. And then what we're going to do with this is try to keep this routine. There's alpha. And then I always recommend just kind of being creature of habit and putting your p-value first and checking that it's smaller than alpha. And it is. Yeah, O2 is smaller than O5. So in other words, that result was probably not a fluke, or there's a less than 5% chance it was a fluke. So you would say that it's significant result. This would lead us to being able to reject the null hypothesis. Like that idea just died, and we can now put that in context that there is enough evidence. There is enough evidence to support that that this is true. That the proportion of delta late arrivals is less than the proportion of united. All right. Make sure that I'm still sharing. I think we're good. All right. And that's the conclusion of the lesson. All I wanted to do before we wrap this up is just right here, just do a quick little like uh, wrap up, mainly just so that when you walk away from this lecture, one of the things that you definitely want to just have in your mind is that p values, anytime that they're smaller, that's a good thing. Smaller means things were not a fluke, that they were more likely to not have happened by random chance. Their significance, and the smaller, the better. The smaller the p value, the less likely it was a fluke, the stronger evidence you have for the alternative. On this one here, I just want you to take maybe a minute, read through it. There's two different p values, and all I want you to do is to match up which one belongs to UV light, which one belongs to the vitamin D. So they were testing in this one to see which of those two would show any evidence or some evidence that it's able to help as a treatment. Um, and as you read through this, you're going to see that one of them showed that it did have the ability to help and that it was probably not a fluke. And then one of them that did not seem successful. So one of these two p values is a good p value, and one of these p values is not a good p value, and one of them belongs to one of the others. But here, I'm just going to be quiet. Yeah, one of those p values is the good p value, and it should go with the thing, the treatment that showed it was effective. And the other one is the bad p value that should go with the thing that didn't seem to work. So again, I'm just going to be quiet for about 30 seconds here, or pause the video. All right. Well, here it goes. Hopefully, you paused the video and you had a chance to read through this one. You could see right here where they say that the UV light showed that it was that they were significantly less likely to get MS. So for that reason, it deserves the good p-value. The really small p-value that it was probably not a fluke, that it showed significant results. And then the not so good p-value, if vitamin D did show any sort of benefit, but they're not really excited about it, it's probably because it was more like that it owned that p-value, like a 47% chance that it was a fluke. All right, but that is your 4.3. Again, I really like that lecture because it gives us the opportunity to have gone through at least three hypothesis tests from start to finish. Again, we're going to be doing more of this as we finish up chapter 4, as we do 5 and 6. And so give it a little bit of time if still needed for it to grow on you and to start becoming just more and more sort of muscle memory, a routine, a process. But with that, I'm going to go ahead and end the recording.